Hello and welcome to the Chemistry Solution. This tutorial is on Hess's law. Remember that enthalpy is a state function, and that means it depends only on the current state of the system. That means that the enthalpy change, or delta H for a reaction, depends only on the initial and final conditions and not the path taken. And so whether a given reaction occurs in one step or in many steps, the enthalpy change remains the same, and this is the basis for Hess's law. Hess's law states that the enthalpy change associated with a reaction carried out in multiple steps is equal to the sum of the enthalpy changes for each individual step. So let's look at an example. Calculate delta H for the following reaction. 2 carbon monoxide plus O2 goes to 2 carbon dioxide. And we'll calculate delta H for this reaction given the two reactions below and their delta H values. So the first step to do this is to manipulate the given equations so that they most closely resemble the equation of interest. So let's look at our first equation. In the reaction of interest, carbon monoxide is on the reactant side. And of the two equations given below, you only see carbon monoxide in one of these equations, and it's on the product side. So what we're going to need to do is to flip this equation around so that carbon monoxide is on the reactant side. So we'll write the equation below, except we'll flip it around. So here we have 2 carbon monoxide going to 2 carbon plus O2. And because we flipped this reaction, we need to flip the sign on delta H. So remember, the delta H value for a reaction written in the opposite direction is of the same magnitude but of opposite sign. And so if we flip the equation, we flip the sign on delta H. So if 2 carbon plus O2 gives us 2 CO and the delta H value is negative 221 kilojoules per mole, then 2 CO going to 2 carbon plus O2 has a delta H value of positive 221 kilojoules per mole. Looking at our reaction of interest, I see that there are 2 moles of CO2 on the product side. And when I look down at our given equations, I see only one of the equations have CO2, the second one. It is on the product side, but there's only 1 mole of CO2 in this reaction. And so for this equation, I need to multiply it by 2. So that I have 2 moles of CO2, so it more closely resembles the reaction of interest. And when I multiply the reaction by 2, I need to multiply the whole equation by 2. And I think it helps to draw parentheses around the entire equation. So this gives us 2 carbon plus 2 O2 gives us 2 CO2. And again, I want to perform the same operation on delta H as I did on the equation. So if I multiplied the equation by 2, I need to multiply the delta H value by 2. So if the reaction carbon plus O2 gives us CO2 had a delta H value of negative 393.5 kilojoules per mole, then the reaction 2 carbon plus 2 O2 gives us 2 CO2 has a delta H value of negative 787 kilojoules per mole. So here I've written my 2 new equations that I modified to more closely resemble my equation of interest. And what you're going to do now is add these 2 equations together, keeping everything on the reactant side, and everything on the product side on the product side. So in my new equation, I have 2CO plus 2C plus 2O2 gives me 2C plus O2 plus 2CO2. And because I added the reactions together, I'm going to add the delta H values together. So the delta H value for this equation is negative 566 kilojoules per mole. But you'll notice that I have some compounds that are the same on both the reactant side and the product side. And so anything that's the same on both sides of the reaction arrow can be canceled out. So I can cancel out my 2 moles of carbon on both the reactants and the product side. And I can also cancel out the 1 mole of O2 on the product side with 1 mole of O2 on the reactant side, leaving me with the final equation 2CO plus O2 goes to 2CO2. And the last thing you need to do is to double check that this equation matches your equation of interest. And in this case it does. So the delta H value for 2CO plus O2 goes to 2CO2 is negative 566 kilojoules per mole. Let's try another example. Calculate delta H for the following reaction. 2N2 plus 5O2 goes to 2N2O5. We're given 3 reactions listed below, and remember the first step is to modify these equations to more closely resemble the equation of interest. Now I think it's always helpful to look for a compound in the reaction of interest that is found only once in your given equations. And in this case you can see that N2O5 that's on the product side in our reaction of interest is in only one of the given equations. And you'll see that it's on the reactant side. So the first thing we need to do is to flip this equation around so that N2O5 is on the product side. The other thing we need to do is to multiply this equation by 2 because our reaction of interest has 2 moles of N2O5 on the product side. And remember, we performed the same operation on delta H as we did on the equation. So if we flipped the equation and multiplied it by 2, we need to flip the sign on delta H and multiply it by 2. This gives us the new reaction 4HNO3 goes to 2N2O5 plus 2H2O, and this reaction has a delta H value of 153 kilojoules per mole. Looking at the bottom equation, I'll see that I have N2 on the reactant side. And in my reaction of interest, I also have N2 on the reactant side. But in my reaction of interest, I have 2 moles of N2 on the reactant side. So in order to make this equation more closely resemble the reaction of interest, I need to multiply the entire equation by 2. Now you'll also notice in this equation that 2 moles of HNO3 are formed on the product side. And when we compare that to the equation that we just modified, we have 4 moles of HNO3 on the reactant side. If you look at our reaction of interest up on the top, you don't see the compound HNO3 anywhere in that equation, which means that you're going to need equal amounts of HNO3 on the reactant side and the product side in order to cancel out in our final equation. So we already knew that we needed to multiply this equation by 2 to give us 2 moles of N2. But you can also look at it that we need to multiply this equation by 2 to give us 4 moles of HNO3, which will eventually cancel out with the 4 moles of HNO3 on the reactant side in our first equation that we modified. And when we multiply the equation by 2, we also need to multiply the delta H value by 2. Now I saved this top equation for last, and it's because neither H2 nor H2O are anywhere to be found in our equation of interest. And so we need to compare this reaction to the reactions that we already modified in order to figure out how to modify this equation in order to cancel out any moles of H2O or H2 gas in our final equation. And what you'll see is that we have 2 moles of H2O on the product side, and we need to modify this third equation in order to cancel those out. So we'll need to flip this equation and multiply it by 2 in order to cancel out H2O by having it on both the reactants and the product side. And you see the same thing with H2 gas. So when we flip this equation and multiply it by 2, remember that we need to do the same thing for delta H. Flip the sign on delta H and multiply it by 2. Now that we have 2 moles of water on the reactant side and the product side, those will cancel out when we add these equations together. And the same thing with our 2 moles of H2 on the reactant side and the product side. Now hopefully we've modified all of our equations correctly. So remember, we add everything on the reactant side and everything on the product side, and then we can cancel out anything that's the same on both sides. Now if you don't want to write all of this out, you can cancel things that are the same on the reactant side and the product side right away before adding your equations together. And so you'll see that we have 4 moles of HNO3 on the reactant side and the product side. We have 2 moles of H2O on the reactant side and the product side. And we have 2 moles of H2 on the reactant side and the product side. Our 1 mole of O2 gas on the product side can cancel with 1 mole of O2 gas on the reactant side, leaving us with 5 moles of O2 on the reactant side. And when we write down what we're left with, we then have an additional 2 moles of N2 on the reactant side and 2 moles of N2O5 on the product side. And when you check, our new equation now matches the equation of interest. And so because we added up these 3 new equations, we also need to add up their delta H values. And so the delta H value for this reaction, 2N2 plus 5O2 goes to 2N2O5, is 29 kilojoules per mole. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.